We started off when we talked about functions discussing linear functions, and now we're going to move on to something called exponential functions, which have something to do with exponents, believe it or not. So for today, our learning goal is I will identify, evaluate, and graph exponential functions. So in order to think about this, we have to flash back to linear functions for a second. And remember, with our linear functions, we had a constant rate of change, which we called slope. And that we were able to find by just figuring out the change in y over the change in x, or the change in our output divided by our change in our input. So in exponential functions, we're not going to have that constant rate of change anymore. So one of the first things we're going to do is we're going to be able to look at a table, and we want to decide if that table is representing an exponential function, a linear function, or maybe neither. So for our first table, if we have our x and our y, where x is our input, y is our output. Let's go 0, 1, 2, 3. And then for our outputs, we have 5, 10, 15, 20. I want to look at my change here. I see that this is going up 5, up 5, up 5 for every change in 1 from x. So this should look pretty familiar to you. This is a linear function. We're changing by the same amount here every time. So if we were to graph this, the slope of this function would be my change in y over my change in x, which is 5 over 1, or 5. So this is linear. But let's look at a different table where we have our x and our y again. X is still going to go 0, 1, 2, 3, but y is going to go 1, 3, 9, 27. So if we look at our change here, x is increasing by 1 every time still, but I'm adding 2, and then I'm adding 6, and then I'm adding, what is that, 16? No, I'm sorry, it's adding 18. Regardless, we are not adding the same thing every time. This does not have a constant rate of change. So right away we know it's not linear. So the next thing we want to look at is we want to see, are we multiplying by the same thing every time? To go from 1 to 3, we multiply by 3. To go from 3 to 9, we multiply by 3. To go from 9 to 27, we multiply by 3. So this is going to be an exponential function. And the reason that we would give is we would say, as x increases by 1, y is multiplied by 3. So to go from one y to the next, we're multiplying every time by 3. With a linear function, we were adding the same thing each time. With exponential, we're multiplying by the same thing each time. And that's the general idea behind exponential functions. So now that you have the general idea behind an exponential function, here is what the most basic form is going to look like. Y equals AB to the x. So this is like the slope-intercept form version of exponential functions. This is going to be the most common way that you see them. And in order for this to happen, a can't be 0, because then the whole thing would be 0, and that would just be a straight line. And b can't be 1, because 1 to any power is just 1. So again, we would just have a straight line. And also, we want b to be greater than 0. If b is negative, then depending on the exponent, it's going to flip-flop back and forth between positive and negative, and it's going to be a mess. So for this, b has to be a positive number greater than 0. That's what positive means, but it can't be equal to 1, and a can't be equal to 1. And you see here that our input, or our x, is up here as the exponent, and that's exactly why this is called an exponential function. So this is the form that you're going to see. So what you will have happen is you're going to be given a function maybe. So say I gave you this function, y equals negative 4 times 2 to the x power. Remember, when we evaluate this for different values for x, we do exponents before multiplication. So we're going to raise 2 to whatever our input is, and then multiply that by negative 4. So something that you might be asked to do is to evaluate this function for, or how about when x equals negative 1, 0, and, oops, I went off the page, negative 1, 0, and 3. So what that means is I'm going to do 3 different substitutions. I'm going to substitute negative 1, I'm going to substitute 0, and I'm going to substitute 3. So let's start off by substituting negative 1. So y equals negative 4 times 2 to the negative 1 power. Remember, when I'm raised to a negative exponent, that means to flip it over or take the fraction. So that would be negative 4 to the 1/2 power. This would be a 2 to the first down here, and I don't need to worry about 2 to the first. Negative 4 times 1/2 is negative 2. So when x equals negative 1, y equals negative 2. Let's evaluate again when x equals 0. So y equals negative 4 times 2 to the 0 power. Remember that anything to the 0 power is 1. So this is just negative 4 times 1, which is negative 4. So the point 0, negative 4 would also be a possibility. Or that would be my solution when x equals 0. And then you can't see, but I also said and 3. So when x equals 3, we would do y equals negative 4 times 2 to the 3rd power. 2 to the 3rd power is 8. So I would get y equals negative 32. So when my input is 3, my output is negative 32. So you can see that as x grows just a little bit, y, in this case, is getting smaller and smaller because they're negatives. But you know, one way that we say it, the negatives are getting bigger. So that is going to be something that happens with exponential functions, where they're going to grow or decrease very quickly. Right here I have 2 on your own problems I'd like you to try. First of all, I want you to evaluate the function y equals 2 times 9 to the x when x equals negative 2, 0, and 1/2. So you got a rational exponent there. And then also I have a table here, 0, 8, 1, 4, 2, 2, and 3, 1. I want you to tell me if this is linear or exponential, and you should be able to back up your answer with a good reason. So hopefully you paused and did these problems on your own, and now we're going to check them. So for this one, I'm going to substitute negative 2 in first. So y equals 2 times 9 to the negative 2. 9 to the negative 2 is 1 over 9 squared, which would be 2 times 1 over 81, or 2 over 81. So a really tiny number. When x equals 0, this is 2 times 9 to the 0. I get 2 times 1, because 9 to the 0 is 1, and I just get 2 there. And when x equals 1/2, y equals 2 times 9 to the 1/2. Remember, the 1/2 power is the same as taking the square root. The square root of 9 is 3, so this is just y equals 2 times 3, which is 6. Now down here, when we're deciding if we have linear or exponential, we notice our x is changing by 1 each time. First, I'm just going to check for linear. I'm subtracting 4, subtracting 2, subtracting 1, so definitely not linear. So then I need to think, what do I need to multiply 8 by to get 4? If I multiply 8 by 1/2, it's the same as dividing by 2, but I'm multiplying by 1/2. 4 times what gives me 2? 4 times 1/2. And 2 times 1/2 gives me 1. So in this case, I'm multiplying by 1/2 as my x increases by 1. So this is going to be exponential. Okay, so we are about halfway done with this section. This is a long one. The next thing that I want to talk to you about is going back to the basic form of an exponential. The y equals ab to the x. Just like when we had linear equations where the different pieces meant things. Remember, we had y equals mx plus b. M was our slope, and b was our y-intercept. The pieces here mean something too. Of course, x is our input, y is our output, or our independent variable, dependent variable, but a and b stand for things also. I do not want you to be confused because there's a b here and there's a b here. Those b's do not mean the same thing at all. I don't know why they insisted on using the same letter. It's just part of math. So this b means something totally different. But let's first start off by trying to figure out what our y-intercept would be in this situation. So remember, our y-intercept is where x equals 0. X equaling 0 is where our graph is going to cross the y-axis. So if I put in 0 for x, this whole term becomes a 1, because anything to the 0 power is 1, which means y is going to equal a times 1, or just a. So our our y-intercept, in this case, when we have an exponential function, is going to be a, or the point 0, a. We can think about this as our y-intercept. We can also think about this as a starting point when we get into like our word problems. A lot of like populations will grow exponentially. Starting point, not starting population. We'll talk about populations growing. We'll talk about like bacteria growing. This 0a is where we're starting off. So that's what that a is going to represent. And then if we go back to when we had our x and our y, 0, 1, 2, 3. If I have an exponential function here, let's just say I'm going up times 3 would be 9, times 3 would be, oh my gosh, 27, times 3 would be 81. So on this one, I just set it up nice and easy, where I'm multiplying by 3 each time. This number right here, the number that I'm multiplying by over and over, this is going to be my b value. So if I have ab to the x, my starting point here, 0, 1, so I'm going to put 1 in for a, and then because I'm multiplying by 3 every time, I'm going to put in a 3 for x. I'm sorry, a 3 for b. So another example, if I had this table, and let's say I start with 2, hope I did this right. 2 times 4 is 8. Oops, times 4. 8 times 4 is 32. 32 times 4 is 128. So I'm multiplying by 4 each time. That means with my function ab to the x, My starting point is 0, 2, so I put in 2 for A, and the repeated multiplication is times 4, so B is 4. So that is how I'm going to write an exponential function based on a table. I can do the same thing when I'm given a situation. If we say a bacteria population increases exponentially and let's say that it goes through, or it can be represented by an exponential function would be another way of saying that, and the graph passes through how about the point 0, 20 and 160. So we know it's exponential, it goes through 0, 20 and 160. So if I make a quick table, I know 0, 20 is a point on there, and 160 is a point on there. So if I know it's exponentially, this is multiplying by 3, which means to go to each next step, I'm multiplying by 3, etc. So to write my equation for this would just be y equals 20, because that's what I'm starting off with. After 0 hours, I didn't really give this context. After 0 hours, I have 20 bacteria, and I'm multiplying by 3 over and over. Or the bacteria, what this is really saying, the bacteria is tripling every hour, which is super disgusting. There's another example kind of like this in your book. It's example 5, so you can go ahead and look at that. And you can see when you're given points, more points, makes it a little easier to see what you're multiplying by each time. But this is the whole idea where 20, or your A, is your starting point, your y-intercept. B is the number that you're repeatedly multiplying. So by 3, by 3, by 3, or by 4, by 4, by 4. Our very last thing to do is to look at some graphs of exponential functions. So I'm going to start off by looking at this function, y equals 3 to the x. And the way that I'm going to graph this is just by using my basic table. Remember, you can always do this. So what I will do is I'll put in these values for x and see what the shape of my graph looks like. When I put in -2 for x, that's 3 to the -2 power, or 1 over 3 squared, which is 1 over 9. If I put in -1, that's 3 to the -1 power, which is 1/3. 0 would be y equals 3 to the 0, which is 1. Anything to the 0 power is 1. If I put in 1, I get 3 to the first power, which is 3. 2 is 3 squared, which is 9. 3 is 3 cubed, which is 27. So you can see I'm multiplying by 3 every time, even to go from 1/9 to 1/3, 1/3 to 1. Every time I'm multiplying by a third. So when I graph these points, I have 0, 1, -1, 1/3 is like right there. -2, 1/9 is going to be really close to 0. So those are my first 3 points. And then I have 1, 3, I have 2, 9, and then 327 is going to be way up there. You can't even see it. It's way off the screen. So when I connect these points, I no longer have a straight line, which makes sense. It's not a linear equation. It's an exponential. So what happens is my graph, if I try and follow my dots, my graph curves and shoots way off into the sky. So this is the general idea of what an exponential looks like. And something to notice here is that I'm actually not going to cross over the x-axis at all, because there's nothing I can put in for x to give me 0. If I put in 0, I get 1. If I put in negative numbers, I just get these fractions that are getting smaller and smaller and smaller. But I'm never actually getting 0 or a negative number. So my domain is going to be all real numbers, but my range is going to be greater than 0, because there's nothing I can put in for x to get 0 or a negative number. So now that we've graphed 3 to the x, let's look and see how the graph of 3 to the x plus 1 compares. And this should look a little familiar to you because it's what we did a little bit earlier with the translating graphs. Remember, 3 to the x is my pink graph. So if when I put in -2 for x, I get 1/9 for 3 to the x. This will be 1 and 1/9. This would be 1/3 plus 1, which is 1 and 1/3. 3 to the 0 is 1 plus 1 is 2. This will be at 4, and 3 squared is 9 plus 1 would be at 10. So when I graph these, graph 1 and 1/9 is about there, 1 and 1/3 is about there. There's 2, 1, 4, and 2, 10 is up here. You can see that my blue graph is just a shift of my pink graph. It's kind of hard to see, but it's really just my pink graph shifted up 1, which is exactly what that +1 does. That's going to be a vertical translation. If this was a -3, then my graph would just be shifted down 3. So something to notice is that this isn't going to change the domain at all. The domain is still x is all real numbers, but my range is what's going to change. Before, my range was all numbers greater than 0, but because my whole graph got shifted up, my range is going to shift up as well, and y is going to be all numbers greater than 1. So that's going to be the difference here. When we tack a number on the end, it's going to vertically shift our graph up or down. And that's how we're going to compare our graphs.